Hey guys, here is day one of section 7.1. So we are clearly starting chapter 7. It's probably going to be the last chapter that we get to start. It is all about the inverse sine, the inverse cosine, and the inverse tangent function. So it's all about your inverse trig functions and how they work and how we can use them, okay? Well, before I start our notes, I just want to review with you inverse functions, just so you remember like what that definition is and what it means to be an inverse. All right, so the simplest definition of the inverse function was that it's a function that has to undo another function, right? So think about how a function works. You plug x into the function does something to it, and it spits an output out, which is y, and create ordered pairs x, y. X went into the function, and y came out. Well, the inverse has to undo whatever that function did. So the way the inverse does that is the inverse takes that output, it takes this y, you plug that y into the inverse will undo whatever the original function did and then spit out the original x that you started with. So remember, y goes into the inverse and x comes out. The ordered pairs get reversed, if you will, with the inverse, right? So x went into the original and y came out. Y goes into the inverse and x has to come out. So that's an inverse function, right? It undoes what the original function did. All right, so keep that in mind. All right, well, let's review a little bit more. All right, well, let's just review some strict definitions. Inverse functions, right? They are functions that undo another function. So the key word is that the inverse, those inverses, they are functions. So they must behave like a function. And the big thing about a function is that each input has exactly one output, right? When you plug 2 into a function and 5 comes out, when you go back in later and plug 2 back in, 5 still has to come out. It's not like you can plug 2 in and now all of a sudden 6 comes out. That wouldn't be a function, right? Each input, each number that you plug in has exactly one number that should come out for that input, all right? So if you remember, not all functions have an inverse that exists, okay? When we were working with inverses, we saw that not all inverses exist, right? Not every function can have an inverse, right? So only a 1-to-1 function can have an inverse. So if you don't remember what a 1-to-1 function is, a 1-to-1 function was a function where both the x's and y's do not repeat. It is a function that passes the vertical line test and it passed the horizontal line test. That way you can prove that the x's and y's don't repeat. And it's important that it's a 1-to-1 function if you want the inverse to exist, all right? So let me show you why it has to be a 1-to-1 function. Why do we want the x's and the y's to not repeat in order to have an inverse that exists, okay? Well, look at this table of values, right? According to this table, when x went in as -2, 5 came out as y, right? 0 went in, 1 came out, 2 went in, 5 came out, 3 went in, 10 came out. Based off of these values, we can say this is a function, okay? Because each number has exactly one output. It's okay if the y's repeated. That was allowed to happen in a function, right? It's okay that 2 went in and 5 came out, and -2 goes in and it also makes a 5 come out. The important part is when I plug 2 back in later, that 5 is still the number that comes out for him, right? That is a function. So this is an example of a function. Okay, it's not 1-to-1, all right? And the reason why we want it to be 1-to-1 is, think about it. What if we tried to create his inverse? The way this inverse would work is that when 10 goes into the inverse, 3 would have to come out. When 5 goes into the inverse, well, that's a problem. Because if 5 went into the inverse, -2 or 2 could come out for him. And that's not a function. So since the y's repeated, his inverse can't exist, okay? So that's why we want it to be 1-to-1. All right, look here. Look at these x and y values. When -3 goes in, 8 came out. When 1 went in, 4 came out. When 5 went in, 0 came out. -3 goes back in, and now a 2 comes out. That's not even a function, right? If -3 can go in and make 2 different numbers come out, that's not a function. So this is an example of something that's not even a function. Okay? And then look here. according to these x and y values, when -4 goes in, 3 comes out. When 1 goes in, 8 comes out. When 5 goes in, 12 comes out. When 8 goes in, 15 comes out. This is definitely a function, and not only is it a function, it's a one-to-one function because none of the x's repeated and then none of the y's repeated. So now it's safe to say that when 15 goes into the inverse, guess what? He's definitely going to spit out 8. When 12 goes into the inverse, it's definitely going to spit out 5. When 8 goes into the inverse, it's definitely going to spit out 1. When 3 goes into the inverse, it's going to spit out -4. This is a one-to-one function because the x's and y's did not repeat, so that when these y's become the x's to the inverse, it's still going to act like a function. So this is an example of a one-to-one function. And this is what we want if we want something to have an inverse that exists, okay? All right, so keep going with that. Let's look at the parabola y equals x squared, okay? If you look at the parabola, he definitely passes the vertical line test. So he himself is definitely a function, right? But it doesn't pass the horizontal line test, which means the y's repeat, and this is not a one-to-one function, right? So if I was to plug, let's say, 1 into the inverse, guess what? A 1 or a -1 could come out of that inverse, and that's not a function. If I was to plug 4 into the inverse, a 2 or a -2 could come out. That's not a function. So this not being a one-to-one function means that his inverse does not exist. This graph cannot have an inverse function unless we restricted the domain. So if you remember, when we were working with inverses, we did this. A whole parabola could not have an inverse. But if I restricted this to the graph of y equals x squared, as long as x is greater than or equal to 0, basically the right side of that parabola, now it passes the VLT and the HLT. Now, this is a one-to-one function. Now, when I plug 1 into the inverse, a 1 will come out. When I plug 4 into the inverse, only a 2 will come out of that inverse. So this is a one-to-one function, and this restricted part of the graph can have an inverse. So that's what's going to happen with your inverse trig functions. If you look at the graph of your trig functions, here's the graph of sine, here's the graph of cosine, and here's the graph of tangent, right? Just real rough sketches. If you look at them, none of these graphs pass the HLT. All of these graphs have y values that repeat on them. I mean, think about it. They're periodic functions. After so many x's go in, the y's start to repeat, right? So these are definitely not one-to-one functions. So technically, the sine, cosine, and tangent should not have inverse functions. But we know that they do. We've seen them on our calculator, right? So the reason why the sine, cosine, and tangent have an inverse is because we restrict their domain. And we only take a portion of their graph to make their inverse exist. So it's very similar to how we make the parabola have an inverse. We have to restrict its domain. So the trig functions also have to get restricted. So it's only going to be a portion of their graph that we get to use to make their inverse exist, okay? So really we have to discover, well, what portions of their graph did we keep? Like here, I kept the right side of the parabola to make the inverse exist. Well, what portions of these graphs did we keep? I call it who survived the cut, okay? What angles and ratios survived the cut of these graphs in order to make their inverse exist, okay? All right, so let me just read that to you just so you can see that again. All right, so the trig functions are not one-to-one functions. So they can only have an inverse function if we restrict the domains, right? If we chop a portion of their graph. So we are only going to use a portion of each trig graph to make its inverse exist. So it's important to see what angles and ratios survived the cut of its graph that we use to make the inverse sine, the inverse cosine, and the inverse tangent functions, okay? Therefore, each inverse trig function will only be able to use ratios and spit out angles that survived the cut of its graph. So here's a spoiler alert for you, just to put it out there. If this is quadrant 1, quadrant 2, quadrant 3, and quadrant 4, right? No quadrant 3 angles survived the cut of any trig graph. So therefore, quadrant 3 angles cannot come out of any inverse trig function. When we start chopping up these graphs to only keep sections of them and make the inverse exist, quadrant 3 angles never survive any of these cuts. So no inverse trig function will ever spit out an angle that landed in quadrant 3. It will not be in their domain. It will have not survived the cut. So just keep that in mind. Quadrant 3 angles are off limits when it comes to the inverse trig functions. And the more we work with them, you'll see how quadrant 3 angles just never get used. They never come out of an inverse trig function. None of them survived the cut of the graph. Okay. All right, perfect. Sorry, I know that took a while, but I wanted to make sure that I went over that with you. So because of that, because of what I just talked about, I'm going to skip the first page of the notes that I give you a copy of because all it does is talk about what I just explained, all right? Also, the back of your notes talks about what I just talked about. So I'm going to skip that too, right? So again, here's going to be your cheat chart. We're going to come back and fill this in at the end, but I'm telling you right now, quadrant 3 angles don't make the cut. They will not come out of an inverse trig function. All right? So real quick, these are the kind of problems they're going to ask you to answer in these problems once you understand how these inverse trig functions work, okay? So again, I'm going to skip this. I'm going to jump right into who survived the cut, all right? And again, today we're only going to work on the inverse sine, okay? All right, here we go. So before we get started with the inverse sine function, let's just go back and look at how the actual sine function worked. All right, let me see if I can move my camera in a little bit now. All right, perfect. Okay. All right, so let's look at the sine function, right? How did the sine function work? Well, the way it originally started was when you took the sine of an angle, the sine function relates the measure of that angle to the ratio of two side lengths O over H, right? And then we redefined that relationship on the unit circle to be a y coordinate over a radius. Either way you want to think of it, okay? All right, so that's how the sine function works. So again, the way it worked is we plugged theta into the sine function. The sine function relates the measure of that angle to the ratio of O over H or Y over R, okay? So the important thing is that an angle went into the sine function and a ratio comes out of him. That's how the trig function works. You plug an angle in and it'll spit a ratio out, okay? Well, again, we have to do this in terms of X and Y to be on the graph. So just instead of theta and O over H or Y over R, let me just rewrite this as Y equals sine X. So X is going to go into the sine function, but he's still going in as an angle, all right? The sine function will take the sine of that angle, which will relate the measure of it to the ratio of two side lengths. So Y will come out, but he's coming out as a ratio, okay? So again, the angle goes in as X and ratio comes out as Y. That is how the sine functions work. You plug an angle in and it'll spit a ratio out. Okay, so now the inverse sine function has to undo that. All right, so the inverse sine function will plug a ratio in. The ratio has to go into the inverse, and then the angle is what comes out of the inverse trig function, right? So the way the inverse, let me show them on the camera, the way the inverse is going to work is now you plug a ratio into the inverse, and it's going to spit an angle out. So angles are what comes out of the inverse trig function. All right, so a ratio goes in and an angle will come out. That is how the inverse will work. All right, so therefore, the inverse sine, we use sine to the -1 as the notation, but it's really not being raised to the -1. That's just how we note the inverse. Just like, you know, when we were doing f of x, the inverse was f inverse of x, f to the negative 1 it looked like. The negative 1 just implies that it's an inverse. So the inverse sine of a ratio will equal an angle, right? So you take the inverse of the ratio goes in, and an angle comes out. I cannot stress that enough, all right? A ratio goes into the inverse, and an angle comes out. But again, not any angle and not any ratio. Only an angle and a ratio that survived the cut of its graph will be able to go in and out of this inverse, okay? All right, so if the original trig function was y equals sine x, then the inverse means we have to switch x and y. So now it's going to be x equals the sine of y. And if you remember, that is the inverse. But the way we like it is we like x to be the one going in and y being the one coming out. So this is known as the implicit form of the inverse, right? It's not solved for y. We have to solve it for y to get it back in the version that we like. And the way we solve it for y, the only way to undo the sine is to take the inverse sine of it. So you take the inverse sine of each side and you wind up canceling them and you get y equals the inverse sine of x. And that is now the explicit form of the inverse. Okay, so that is the inverse trig function, all right, where a ratio will go in as x and an angle will come out as y. That's how the inverse trig function works, okay? All right, so now we will need to graph the sine function to show how the inverse sine function is defined. We have to see who survives the cut. What portion of the sine graph did we keep to make its inverse exist, okay? All right, so what I did is I went ahead and I graphed the inverse sine function, not inverse, I'm sorry, I graphed the sine function for us, just to save us a little bit of time on the video, okay? So here is the graph of sine, right? Here is your sine wave. All right, you plug in 0, the sine of it is 0. You plug in pi over 4, the sine of pi over 4 is root 2 over 2. You plug in pi over 2, the sine of pi over 2 is 1, and so on. So I just filled in your chart and I graphed the sine function. All right, well, here's what's going to happen. So right now, your sine wave, right, you can tell right now that it passes the vertical line test, meaning it is a function, but it doesn't pass the horizontal line test, which means it's not one-to-one. Look at all of these y values that repeat on the graph. All of these are repeated y values. So this is not a one-to-one function. So if you just look at it right now, if you look, this portion of the graph from 0 to pi over 2, these are all your quadrant 1 angles and ratios. They live on this part of the graph, right? From 0 to pi over 2, because those would have been angles that you found in quadrant 1. All right, and then on this portion of the graph, from pi over 2 to pi, these are all of your quadrant 2 angles and ratios, okay? From pi to 3 pi over 2, this portion of your graph right here, these are all of your quadrant 3 angles and ratios. And then from 3 pi over 2 to 2 pi right here, these are all of your quadrant 4 angles and ratios. And that is one complete sine wave, right? So here are your quadrant 1 angles and ratios. Here are your quadrant 2 angles and ratios, your quadrant 3, and your quadrant 4 angles and ratios. So right now, this graph or this function can't have an inverse because he's not one-to-one. So we're going to have to like chop it off in a section where it does pass the HLT. All right, and we want to start right at the origin. So if I start right at the origin and kind of just start like on each little leg of the graph, if you will, from here to here, from here to here, from here to here, and so on, right? Okay, well, where does it keep passing the HLT? So if I look right here, just on this leg, right? Does it pass the HLT? Yes, 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 yes. But the minute I get up here and the minute I go over this hump, will it continue to pass the HLT? No, because it'll cross here and here. So we're going to have to chop the graph right here at pi over 2. I can't go past pi over 2, otherwise it will stop passing the HLT and the y's will start to repeat. All right, well, since I can't go this way anymore, I'm going to have to go backwards, all right? So that means if I start going this direction, right, which if you notice, from 0 to negative pi over 2 on this leg, these are quadrant 4 angles from 0 to negative pi over 2. Now we're rotating clockwise around the unit circle. All right, so now if I try to pass the HLT, is it passing? Yes, 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 yes. The minute you come around this turn, though, will it continue to pass the HLT? No. So you're going to have to chop it here at negative pi over 2. So the portion of the graph that we end up keeping to make this inverse exist, I'm just trying to get something here, is from here to here. If I chop the graph right now from negative pi over 2 to pi over 2, does he pass the HLT? Yes. So this is the portion of the sine graph that we keep to make his inverse exist. So if you notice, only angles between 0 and pi over 2, quadrant 1 angles, and angles between 0 and negative pi over 2, your quadrant 4 angles, survive the cut of his graph, which means the inverse sine function is only going to be able to spit out quadrant 1 angles or quadrant 4 angles, because those are the only angles that live on the portion of his graph that survived the cut. Angles between pi over 2 and negative pi over 2. And ratios between 1 and negative 1 survived, okay? All right, so just keep that in mind. This is the portion of the sine graph that we keep to make his inverse exist. So quadrant 1 and quadrant 4 angles are the angles who survived the cut, okay? All right, now, I maybe should have done this before, but I apologize. So look at the sine function before I chopped it. If I plug an angle between 0 and pi over 2 in, right? If I plug an angle between 0 and pi over 2 in, a ratio between 0 and 1 comes out, okay? That's the way that leg of the graph works. If I plug an angle between pi over 2 and pi into this trig function, a ratio between 1 and 0 comes out. I should have done this. Okay, keep going. If I plug an angle between pi and 3 pi over 2, if I plug an angle between pi and 3 pi over 2 in, a ratio between 0 and negative 1 comes out. This is how the original function worked. If I plug an angle between 3 pi over 2 and 2 pi in, right, an angle between 3 pi over 2 and 2 pi, a ratio between negative 1 and 0 comes out. Okay, if I plug an angle between 0 and negative pi over 2 in, if I plug an angle between 0 and negative pi over 2 in, a ratio between 0 and negative 1 comes out. Okay, sorry, I should have done that first. So that's how the original trig function worked, right? These angles went in and these ratios came out. Well, like I said, now we have to chop the graph. Does this graph have an inverse that exists? Technically, no, it doesn't. In its first original form, it should not have an inverse, okay? But if we restrict the domain, then the inverse can exist. So remember the graph of a parabola, how we had to cut it off? Same thing happens here. So we need to take a smooth, continuous portion of the graph where the inverse can exist. So like I said, and I showed you, where can we take this smooth, continuous portion from its graph that will allow it to pass the HLT and allow it to have an inverse, right? Well, I've already kind of jumped the gun a little bit, and I showed you that you're going to cut the domain from negative pi over 2 to positive pi over 2. And that's going to be the portion of the graph that we keep to make his inverse exist. All right, so if we restrict the domain from negative pi over 2 to pi over 2, then the inverse can exist. And that's exactly what we're going to do. This is the portion of his graph that is going to allow the sine function to have an inverse. So just to repeat, only quadrant 1 and quadrant 4 angles survived the cut of his graph. So angles from pi over 2 to negative pi over 2, and ratios between 1 and negative 1 survived. That is who is going to live on the portion of this graph to make it have an inverse. Okay. So again, as you can see, like I said in the beginning, quadrant 3 angles did not survive the cut of his graph. In fact, quadrant 2 angles did not survive the cut of the inverse sine's graph, right? So, or the sine's graph. Only quadrant 1 and quadrant 4 angles. Okay. All right, hang on, let me get my next sheet. Okay. Therefore, the inverse sine function only exists for angles between negative pi over 2 and pi over 2, which are angles found in quadrant 1 and quadrant 4. All right, so this is what the graph of the inverse sine function is going to look like, right? So now we're going to plug a ratio in as x, and an angle will come out of the inverse sine, because that's who comes out of the inverse trig functions. Angles. Inverse trig functions find angles. All right, also, if you ever see y equals arc sine is just another way of saying sine to the negative 1. Arc sine is kind of like just an old-fashioned way of saying the inverse sine, but it means the same thing, okay? All right, well, watch this. So if you look at the angles that survived his graph's cut, right? We said this is going to survive. So 0, 0 survived the cut. So switch x and y. 0, 0 will live on the inverse's graph. And remember, the ratio is going to go in as x, and the angle are going to come out as y. So we said angles between pi over 2 and negative pi over 2 survived his cut. And we said ratios between 1 and negative 1 survived his cut. Okay, let me go back. All right, well, what other points survived the cut of his graph, right? So the point pi over 4 root 2 over 2. That was the ratio in your chart. When pi over 4 went in, root 2 over 2 came out. So pi over 4 root 2 over 2 survived the cut. And root 2 over 2 was about 0.7. So pi over 4 went in, and about 0.7 came out. So now 0.7 is going to go into the inverse, and pi over 4 is going to come out. So now about 0.7 goes in, and pi over 4 comes out. So that lives on the graph of the inverse. All right? Who else lives on the graph of the inverse? Well, the point pi over 2, 1 lived on the original function's graph. So now a ratio of 1 will go into the inverse, and an angle of pi over 2 will come out. So now a ratio of 1 goes into the inverse, and the angle pi over 2 comes out. Okay? All right, who else survived? I'll go back to the graph. Okay? So the point negative pi over 4, negative root 2 over 2 lived on the original function's graph. So now negative root 2 over 2, negative pi over 4 lives on the inverse. So now a ratio of negative root 2 over 2, which is about negative 0.7, goes in, and a angle of negative pi over 4 comes out. Okay, so that's a point on the inverse. And then last, another point on the graph that survived the cut was the point negative pi over 2, negative 1. The angle negative pi over 2 went in, and a ratio of negative 1 came out. So now a ratio of negative 1 will go into the inverse, and the angle negative pi over 2 will come out of that inverse. So now the ratio negative 1 goes in to the inverse, and the angle negative pi over 2 comes out. So now this is the graph of the inverse sine function. That is what it looks like. And again, it's just a chopped version. It's not infinite because only a portion of the original graph made the inverse exist. So this is the graph of the inverse sine function. So now we can read it. Look what it says, all right? So it says, if I plug a ratio between 0 and 1 in, right? So if I plug a ratio between 0 and 1 in, right? If I plug any one of these ratios in, right? I plug this ratio in, that angle comes out. I plug this ratio in, that angle comes out. I plug this ratio in, that angle comes out, right? If I plug a ratio between 0 and 1 in, then an angle between 0 and pi over 2 will come out. Okay, so therefore, the angle would be in, well, if the angle was between 0 and pi over 2, it would have been a quadrant 1 angle. And that's what we said. Quadrant 1 angles survived the cut of his graph. So when we go to do these problems, when you take the inverse sine of a positive ratio between 0 and 1, it's going to spit out an angle between 0 and pi over 2. It's going to spit out an angle that landed in quadrant 1. So then you're going to put your triangle or angle that we're using in whatever problem they've given us, put that angle or triangle in quadrant 1, because that's where that angle would have been. If you take the inverse sine of any ratio between 0 and 1, it's going to spit out an angle between 0 and pi over 2, okay? All right, look here. If I plug a ratio between 0 and negative 1 into the inverse sine, right? If you plug a ratio between 0 and negative 1. If I plug this ratio in, that angle comes out. If I plug this ratio in, that angle comes out. If I plug this ratio in, that angle comes out. If I plug this ratio in, that angle comes out, right? If I plug a ratio between 0 and negative 1 in, then an angle between 0 and negative pi over 2 comes out. And where do angles between 0 and negative pi over 2 land? They land in quadrant 4. Those are the quadrant 4 angles that survived the cut of his graph. All right, so therefore the angle would be in quadrant 4. All right, again, you plug any one of these ratios between 0 and negative 1 in, and it's going to spit an angle between 0 and negative pi over 2 out. So therefore, in that type of problem, if you take the inverse sine of that negative ratio, the answer is some quadrant 4 angle. So put the angle or put the triangle that you need to build to solve the problem in quadrant 4. And again, this will make more sense when we start solving more problems. Okay, all right, so here's the deal. This is what you need to remember. The inverse sine function, it's the only function we're going to work with today, can only spit out angles between negative 90 degrees and 90, if you want to think of it in degrees, or it can only spit out angles between negative pi over 2 and pi over 2 radians. So any answer to an inverse sine question can only be an angle between negative pi over 2 and pi over 2. Those are the only angles that live on the portion of the graph that we kept to make his inverse exist. So a lot of times you'll see me do this, right? I'll kind of draw up a little coordinate plane. Here's pi over 2, here's 90 degrees, here's negative pi over 2. Here's negative 90 degrees. The inverse sine function will only spit out angles from here to here. It'll only spit out quadrant 1 angles or quadrant 4 angles. And those quadrant 4 angles are angles from 0 to negative pi over 2. This portion got chopped and this portion got chopped. None of these angles exist on the portion of his graph that we kept. All right, so these are the only angles that can come out of the inverse sine function. Angles between pi over 2 and negative pi over 2. Okay, so watch. Now you have kind of clues. All right, so quadrant 1 and quadrant 4 angles are our angles for the inverse sine function. So therefore, if you take the inverse sine of 3/5, 3/5 is a positive ratio between 0 and 1. So if I take the inverse sine of positive 3/5, I know that the answer will be found as some angle between 0 and pi over 2. If I take the inverse sine of some positive ratio between 0 and 1, that's what 3/5 is, it's going to spit out some angle between 0 and pi over 2, which will be an angle found in quadrant 1. Okay? And again, you can even ask your calculator now. What is the inverse sine of 3/5? Now, my calculator is in radians, so it's going to give me the answer in radians. So what is the inverse sine of 3/5? It better be an angle in quadrant 1. And it is telling me it is 0.64 radians. That is the angle. Well, again, think about it. Pi over 2 is 180, pi over 2. It's pi divided by 2. 3.14 divided by 2 is 1.57 radians. So guys, guess what? 0.64 radians definitely lives in between 0 and 1.57. It is a quadrant 1 angle. And again, let me go into degrees so you can see that it's definitely a quadrant 1 angle. Let me just switch to degrees. Enter, second, quit. Now I'm going to do the inverse sine of 3/5 again, and now it'll give me the answer in degrees. Oops. And it's about 36, 37 degrees. And that's an angle that would have landed in quadrant 1. Because when you take the inverse sine of a positive ratio between 0 and 1, the inverse sine is going to spit out an angle between 0 and 90 degrees, between 0 and pi over 2 radians. All right, look here. So therefore, if they're asking you, what's the inverse sine of negative 2/3? If you take the inverse sine of a negative ratio between 0 and 1, between 0 and negative 1, it's going to spit out an angle between 0 and negative pi over 2, some quadrant 4 angle. All right, it would have been a quadrant that was found, an angle that was found in quadrant 4, okay? So watch. I'll do it in degrees. What is the inverse sine? It's going to be something between 0 and negative 90. What is the inverse sine of negative 2/3? It's negative 42 degrees-ish. And that's definitely an angle between 0 and negative 90 degrees. It is totally giving you a quadrant 4 angle between 0 and negative pi over 2. All right, and again, let me just get your answer in radians because that's what we're going to use. Let me just go back to radians. Yep. And now, second quit, the inverse sine of negative 2/3 in radians is about negative 0.73 radians. And if you remember, negative pi over 2, pi divided by 2, it's negative 1.57. So 0 to negative 1.57 radians, negative 0.73 falls right in there between 0 and negative 1.57. It's some quadrant 4 angle. All right, so again, the answer to an inverse sine question can only be an angle between pi over 2 and negative pi over 2. Only these angles survived the cut of his graph. All right, this video has gotten ridiculously long, but like I said, I have to kind of get into the intricacies of who stays and who got cut. All right, so the last page of your notes is all the examples. I'm going to stop my video because it's going to cut me off anyway, and I'll do the examples in a separate video. All right, I'll be back.